Hello everybody, my name is Abdullah. I'm a Ph.D. student of the Department of Geosciences at the University of Padua. In my research project, we're working to develop a process to integrate carbon dioxide mineralization with the mining activity. So carbon dioxide mineralization is the process of sequestering carbon dioxide in a form of stable carbonate mineral. So if we have the metal oxide that reacts with carbon dioxide, we will have the corresponding carbonate mineral and we produce heat. The metal can be magnesium, calcium, or iron. The advantage of this process is that it represents a permanent and safe storage of carbon dioxide. So basically there is no way for the sequestered carbon to be released again into the atmosphere, at least in the near future. Moreover, our feedstock materials are distributed worldwide. The feedstock materials can be rocks such as mafic, ultramafic, or even wollastonite. It can be mine tailing, it can be brine, or even industrial waste. And our aim is to sequester carbon dioxide, to recover the energy relevant element, and to produce some sellable byproducts such as carbonate and silica. So our aim in this project is to develop a process. Basically, we will start with wollastonite mine tailing that will undergo the dissolution reaction. Once we have the complete dissolution, we will introduce carbon dioxide to precipitate the carbonate. Then we will have a membrane separation. So in the membrane filtration, the carbonate and silica will be rejected and our critical element will be retrieved downstream. But it's not that easy, and for sure we will have some challenges. First, if we think about the dissolution rate, this is the limiting step in this process. So the process happens in nature, but it needs thousands of years. We're talking about geological time scale, and we don't have that time. So we need to find a way to accelerate the dissolution rate to be happened within a few days at standard condition. So no energy input should be used because we don't want to increase the cost and we don't want to produce carbon dioxide. Moreover, if we think about critical elements, so these elements are already found in nature, but their concentrations are very low. And in our case, we're dealing with mine tailing. So the concentrations are much lower. And our rule is to develop a process to recover this element from something that is used to be waste material. Then if we think about our byproduct, carbonate and silica, we need somehow to control their properties. Otherwise, we can't sell them. So their properties should meet the industry standards. Then we need to model the process of dissolution, precipitation. So we need to find a way to model this process. And finally, we need to understand our chemical reaction. So we need to understand our reaction kinetics. We need to understand what are the factors that control our reaction and how to optimize these factors. Then our approach to tackle this problem and to answer all these questions through laboratory experiments. So we will have some experiments using a batch reactor that is monitored online with some probes, conductivity, pH, temperature, pressure, and we will also have Raman spectroscopy. But we also will have some offline measurement with the ICP-MS. So we're thinking of using, let's say, weak organic acids, and we're also thinking of using some microorganisms. Then everything has been done in the laboratory should be described with a mathematical model. So this model should describe accurately our chemical reaction, what happens in the lab, and should predict the state of the system under untested conditions.